Here, I'm Dr. TV Geeta, and I'm going to talk to you in this video about how AI finds hidden patterns in data. It's a very interesting concept, and I'm going to give you this video through my YouTube channel, AI Nexus. Please do subscribe to it. I'm Dr. TV Geeta, and I will be explaining clustering and dimensionality reduction in a very simple manner. So, clustering is nothing but grouping similar data points, while dimensionality reduction is reducing complex data to simpler form by keeping what matters and removing what is extra. Clustering is grouping data based on similarity. So the goal here is to put similar items into the same group. But remember, there are no labels. There are no labels given beforehand, only features are given. And actually, the model does a self-discovery, discovers structure on its own. Now, why does clustering matter? There is no need for label data. This is very important because label data is a costly affair. It reveals hidden patterns in the data. It enables segmentation of the data. It simplifies complex data, and it supports business strategy. Real world examples include customer segmentation, image compression, fraud detection, which is then later on given to other models, face recognition, and medical gene analysis. Let's understand clustering with a simple example. Imagine a school playground. You have a group of football players sitting together, group who's studying sitting together, and some children who are eating snacks sitting together. Now, the teacher does not assign them to groups. They group themselves because of the interest. This is basically clustering. So clustering measures similarity between data points using some similarity score, and then similar data points are grouped together as shown here. Now, how does it work? You would represent the data as points in space, as we already discussed in the previous videos. The more features you have, the higher dimension will be this point in space. The understanding is that those points will be more similar. How do you measure similarity? Using some similarity score to measure the distance between points. And then you look for dense regions, maximum similarity within the cluster and minimum similarity across the cluster. So based on this, they are separated into groups. The meaning of each group is interpreted only later. So actually, what is the problem we are solving? We are given unlabeled data. How can we discover natural groupings inside it? There is no target variable, there is no prediction. We are just discovering structure. The mathematical perspective is we are partitioning the data into groups so that points within a group are very similar and across groups are not similar. And the geometry is the dense regions are the clusters, the sparse gaps are the boundaries, and outliers is the noise. So how to measure success? So you can have compactness. Points inside a cluster should be similar. Separation, clusters should be distinct. Okay. Stability, small data changes should not change or destroy the structure. And clusters should make domain sense. That is, interpretability should be possible. That depends on the model, and it also depends on what features you give. And final summary is clustering is an unsupervised learning technique that discovers natural groupings in data without using any labels. Now, clustering, real world example, real customer segmentation, retail customer segmentation. So you have raw data, it could be customer ID, age, monthly spend, visits per month, and what is the product variety. And the features could be spending, visit frequency, product variety. This is both these are decided by the designer. And then you use a clustering model and you will get a finite output. Please remember, you will only get the clusters. You are giving it some value. So it could be high spenders, frequent visits, low spenders, rare visits, and medium spenders. So output is not given beforehand. The groups are discovered. And let's take an example of medical patient clustering. So the raw data could be patient ID, BP, sugar, BMI, cholesterol. The features derived could be high metabolic profile, obesity risk pattern, diabetes risk pattern, cardiovascular risk pattern. And based on these features, they are clustered. And the final output could be high risk group, moderate risk group, and low risk group. Groups are given, we have to interpret it. And this helps doctors decide better treatment strategies. Next, we go to the next technique, which is dimensionality reduction. So the idea here is that you start with high dimensional data and then you find patterns and correlations and combine these features that are correlated and create low dimensional features. So this can be used later on for clustering, classification, visualization. So why should we do this? Because simpler models generalize better. So high dimension means more noise, more overfitting, unstable distances. Lower dimension, cleaner structure, better clustering, better generalization. In machine learning, in computer science in general, we talk about something called Kamp's razor, which says the simpler the representation, it is better learning always. Okay, so try to find as simple as model as possible which fits the data. So how do we measure success? We measure success is the maximum information that is preserved with minimum dimensions. So you have variance. How much variance is actually retained from the high dimension to low dimension? A mean square difference after reconstruction between the high dimensional data and the low. And neighborhood preservation. If neighbors in high dimensional, they should also be neighbors in the low dimension. As a mathematical problem, we are finding a transformation that maps high dimensional to low dimensional while still preserving the structure. So you should have a dimensional reduction mindset. Are some features correlated? Are some just noise? Is it a real structure? Much simpler. So it is often said that high dimension often hide a simpler structure. So the mindset is we have to ask, is all this information really necessary? There is a misconception that don't assume that this misconception that is the more the features, more is the knowledge, better is your output. That's not true. Instead, ask, are some features correlated? Are some just noise? Is the real structure much simpler? So high dimensional data, many features, hidden simpler structures, underlying patterns. Dimensionality reduction tries to keep what actually matters. Because of this, you get better results when you're using this data that has been reduced in dimension for better clustering, classification, and visualization. In almost all real world cases, this is true. Okay. So let's take some examples of dimensionality reduction. One is original image, then you dimensionality reduction it by keeping only the top components. The restructure will have a similar quality. The advantage is the final output will have a smaller storage. Fraud detection processing, transaction data is high dimensional. Dimensionality reduction you do to remove the redundancy. And then the final output you can use for other models for fraud detection. So what is the success of dimensionality reduction? Reduce storage, use less space, minimal visual loss, quality stays still similar, and better performance because other models have less data to deal with, so faster training and more accurate. There are two types of dimensionality reduction: feature selection and feature extraction. Feature selection, you select the most important features. For example, from 20 features, you select only 5. It's just a toy example I'm giving you. Feature extraction, you take 2 features and create new features. For example, height plus weight can be another component. So it's an unsupervised technique. There are no labels. You are still finding the structure in the data. The key takeaway is simpler data leads to better insights.